problems. And the key word here is mixed. So this is why for beginning we drop it and to consider boundary value problem. As to boundary value problem, we will solve them only for Laplacians and only for two-dimensional Laplacian. So that is the Laplace equation, right? So here x and y, they are coordinate, and y is a function to be determined. And this equation is solved in a region that D. So we need to know where it's solved. The solution of that equation for a given region is not unique, and we need to specify it. To do this, we impose the so-called boundary conditions. Boundary conditions. Boundary conditions, there are several types, actually many types of boundary conditions, but we will work with only two of them. Either the function itself is given on the boundary, and boundary, not like that, so D is a region, and the partial derivative of D is the boundary. So this condition is known as the Dirichlet condition. Another condition, and this condition is imposed on on the whole boundary. So at each point of D with S, which is the so-called curvilinear coordinate along the boundary, the function f of S is given. Second condition, most famous, is condition for the derivative. So derivative, normal derivative on the boundary is given. Normal derivative, this is the normal to the boundary, and we differentiate the function with in normal direction. So that is means we calculate gradient and multiply it by normal. Gradient is phi x, phi y. And again on the boundary, and this is Neumann condition. Neumann boundary condition. So the two main boundary conditions. They are most famous, in addition to these two, it's a so-called third order, or they remember it's called Korobkin condition, when there is a combination between the normal derivative and the function itself. In particular, the waterways on the surface, waterways with the count for gravity, they described by that condition. So the condition. But these conditions are two main. So the boundary condition plus boundary conditions plus Laplacian equation, all together they are known as boundary value problem. As to boundary value problems, if the boundary, okay, I write it over here. If boundary is smooth and f of c or g of s also is smooth. So we can calculate as many derivatives as possible, or there is a limit for derivative, but they are smooth. Then the solution is also smooth. Is also smooth up to the boundary. Inside the region, the solution is always smooth. Because the second derivative, they should be balanced, so we can differentiate the function inside the domain as many times as we can, as we want. But on the boundary, that is another story. And smoothness close to the boundary and on the boundary depends on the curve. I mean, on the boundary itself. If the boundary is with corner points or with cusp, then there could be troubles in terms of the smoothness and also the function. I mean, the solution on the boundary or normal derivative on the boundary, they should be smooth to provide a smooth solution. Then, for Dirichlet boundary value problem, this problem has unique solution. Unique solution. Solution of this problem is unique. So if function is by Laplace equation and is given on the boundary more or less smooth, the function on the boundary is smooth, then the solution is unique. As to the Neumann boundary value problem, if phi xy plus c is solution. So if phi is solution, then we add any constant, and it's again the solution. So it's not unique solution, but we know the up to which order, up to which level the solution is not unique. Now, that is the boundary value problem. As to mixed boundary value problem, I'll explain main difficulties. Mixed boundary value problem, they are again for Laplace equation and only two-dimensional. Only two-dimensional problems are considered. And the boundary is divided into pieces. Let's say two pieces. That is the, say, gamma 2, and on this part of the boundary, normal derivative is given. And on the rest of the boundary, gamma 1, function itself is given. So that is the mixed boundary value problem. On different part of the boundary, different type of the boundary conditions of different type are imposed. So that is the scheduled, it's gamma 2. That for Neumann condition, and that is the rest of the boundary gamma 1 for the Dirichlet condition. So altogether, region B consists of two parts, but there are no intervals between them. So this problem is different. First of all, if boundary is smooth, GS and FS are smooth, the solution is singular in general. In general means that only if, in addition to their smoothness, these two functions satisfy extra integral conditions, so there is some equalities with integrals on their functions, only then the solution is finite. In general, is unbounded. Even everything is smooth, everything is perfect, but that is the problem. In particular, this is the reason why that mixed boundary value problem are difficult for numerical solutions. Because you need to incorporate that singularity, and you need to know that singularity, and either whatever may happen, if you do not account for that singularity and you reduce the mesh, you approach to that point at which the boundary condition changes type, then the your solution just blow up. So it's diverged when you reduce the size. The point where the solution is not smooth is that point. And in general, the singularity over there depends on the angle. If there is angle on the boundary, and then it depends on the value of that angle, and depends on the values on both sides of the. No, it depends on the global boundary condition. It's not local property; it's global property. If the boundary is smooth, means that the the angle, the tangential angle is continuous at these points, then in general, say again in general, the singularity is a square root. So once we approach to this point, then phi increases 1 divided by square root of a distance from that point in general. And the same over there. Then the solution is not unique. So that is the first one. Second, the solution is not unique. Means that there are many solutions with f equal to 0 and g equal to 0. So if everything is 0, there are still 0 solutions. They are so called that we can say eigenvalue or eigensolutions. So there are no forcing, there are still solutions. All that solution, they are singular. But because the singular in one or another way. Because the in general solution is also singular, and particular solutions they are also singular. So this is the solutions are allowed and they should be considered. Right? They can be very singular indeed. Yeah. So that one, and then for the general shape, we can solve this problem only numerically, right? With boundary elements or finite elements or finite differences. But as I said, all of them they have difficulties with taking that point. In particular, for finite elements, they are now so-called super elements. Super finite elements, which are different from the elements you use as approximation you use inside the region and on the rest of the boundary. Close to that point where the boundary condition change their type, the super finite elements, they account for that singularity in there. So they use the special functions in particular that square root of the distance to approximate the solution with unknown coefficients which are determined by kind of assembling all that finite elements. So, but there is a technique which is kind of that is what's in this lecture, and it was explained. That is the technique is called conformal mapping. If there is a mapping, and it's proved a long time ago, it's so-called Riemann theorem, that any region can be mapped onto the circle. And because any circle can be mapped on the lower half plane, and it's kind of convenient for me to use this lower half plane, I'm saying that that boundary can be mapped onto the lower half plane with that shadowed boundary corresponding to interval from -1 to 1. The conformal mapping is defined up to say constants, up to say points. So you can take any say points and you should assign where this point goes, say points. So say points 1, 2, and another point, I take it somewhere over here, I put it, I give it name C, and this point goes to infinity. Goes to infinity. One point goes to infinity, and this 2 point goes to plus and minus 1 on the real axis. So that is this xi, that is eta, and this is the x and y coordinates. So the conformal mapping is defined, not defined, but this is the relation between the Cartesian coordinate in the original plane, in the original formulation, and psi and eta coordinate in the auxiliary plane, which is convenient for solution of that problem. So we, in this way, by introducing conformal mapping, the problem is divided into two. First of all, first problem is geometrical problem, is geometry. It's nothing about the, is it the function f, function g, is there any physical meaning? We're just concerned with the shape. One shape, which is given, we map onto the lower half plane. That is geometry. To do that, we also need to solve boundary value problems, or in one or another way, or you can use handbooks with the tables of that mapping. If the domain is more or less simple, then it's just given in analytical form. If not, then there are different techniques. In particular, if the domain is polygonal, made of straight lines, then there is a famous Schwarz-Christoph transformation, but it's still some integrals and other things, but it's a this formula, you can solve it, you can do this, right? Potentially, you can approximate any shape by polynomial, by polygonal shape, and to use that potentially. Then, what's happening if function f, the function we need to find, is the solution of the Laplace equation? Then, after transformation, new function, let's say this new function is big phi psi eta, which is equal to little phi eigenvalue function of x psi eta and y psi eta. This function will satisfy the Laplace equation again. So that is the characteristic of the conformal mapping. Basically, conformal mapping means that if you take two lines at certain angle alpha, then this angle is mapped to the same angle. I mean, the transformation keeps the angle. So this very special transformation, and also due to some reasons, it's given only by analytic functions and the functions which also are solutions of the Laplace equation. Then the function is given on the gamma 1. So gamma 1 is over here. So potentially, not potentially, but actually we can find the function big F, which comes from that one, big S, little s, and then the if small phi is given on gamma 1, then small phi will be given on that interval on that interval. Then, as I said, the conformal mapping is preserve the angles. Then it also preserves the angle between tangent to the boundary and the normal to the boundary. This means that normal derivative goes to normal derivative, and the boundary condition over here, it can be formulated in terms of the normal derivative. So by using that conformal mapping, which is not so much concerned with the position of the contact point, is it a mixed boundary value problem or not, is it normal boundary value problem, we always can use problem to the simpler one only for the lower half plane. There should be boundary conditions, not boundary condition in the far field. So always, because if we have the infinity, there should be condition at the infinity. That boundary condition comes from that point. C goes to infinity. So this means we require that phi tends to f of psi, and f of psi, if we look at that, it's equal to f at c as psi tends to. So that is the constant value of f at that point c. Actually, point c can be chosen arbitrarily, as you want, just for convenience. If the problem is symmetric, it's convenient to take this point as the line of symmetry, for example. If not, there are other options, but generally it's any. Okay, so that is the problem we will continue with. So that is picture for mixed boundary value problem in general shape. Then by using conformal mapping, we reduce the problem for to that for the lower half plane. There are some limitations. First of all, there are only one interval with derive condition and one interval with normal condition. It's not necessarily the case. There could be several intervals, right? Many. Then there will be several intervals on the real axis, because the boundary goes to real axis. Right? So that intervals, all of them will be represented by intervals of real axis. It's not a problem. So all this problem can be solved. Then what else? Yeah, if the boundary conditions are different, for example that one, which is for example for floating plates, then we cannot solve the problem completely in this way, but we can reduce this problem to the integral equation onto the plate, onto each floating plate. So that is the could be easier because we account for the not only for the rest of the boundary condition, but we account also for behavior of the solution at the that is the floating plate over here. So always something happening. That in particular, normal derivative is not continuous at that point if we think about floating plates, right? But yeah, we can account for that, and we can derive. Not derive, I think we can make a better algorithm to solve that problem. Alright, so that is the problem. There could be many intervals. And as to say applications, one of the applications is so-called floating plate impact problem. That problem, we do not use this part about boundary values because the boundary value problems we are finished with them. So first problem, impact of floating plate. Impact of floating plate is going like this. One, yes. There is the plate, floating plate of zero draft. So all conditions are on the surface, and initially the fluid is at rest, and then the plate starts to move with a given velocity with its impact. Instantly it starts to move at given velocity. In this problem, the boundary condition, dynamic boundary condition on the free surface, which is pressure equal to zero, it can be so-called integrated in time, and we arrive at the condition that potential equal to zero. Gravity doesn't play a role in this problem because we are saying it's so quick, impact is so quick that the gravity or fluid have no time to understand that it has inertia, has the weight. Then over here, particles of liquid, they move with the same speed, normal speed, as the plate. So the boundary condition is vertical velocity, dy, where y is velocity potential is equal to minus v. Minus velocity because it's down. So that is the boundary value problem we need to solve. Say that is the interval. That is the plate, so minus L12, so total length is 2L. If the plate in addition rotates, this boundary condition becomes more complicated. There should be plus alpha, say x. If it's rotated. If it's flexible, so if it's can be deformed, then it will be W of x deflection caused by impact. So it's instant problem. So the phi over here, that phi xy is equal to, say, velocity potential x, y, say, t equal to 0. So just after the impact. Because it's impact, and instantly the velocity, the flow, the state of the fluid change from the rest to a certain flow, and this flow is described by this problem. So the say Any problem with free surface? Let us say free surface. And that is the body surface. That is the body. In each problem, so they exist for ships or any others. On the free surface, the boundary condition is for the pressure, say pressure is equal to constant, plus so-called kinematic boundary condition, plus kinematic boundary condition. That if we solve this problem by steps in time, so at each step we are saying that the potential on the boundary, potential on the free surface is given. Then normal derivative or normal velocity on the body surface we are saying is given. And then we arrive to the same mixed boundary value problem. So that point, the points, they are contact points, say, or points, mathematically speaking, points at which the boundary condition change their type, they points of singularity. And potentially, they can be troubles for solution of that problem, for numerical solution. So that is the example, and then to start with, solution, to explain how to solve the mixed boundary value problem, we start with Dirichlet problem. So first we start Dirichlet boundary value problem. That is the problem for potential, and potential is equal to function, say f of x at the infinity, f of x decays at the infinity, and also the solution decays at x squared plus y squared tends to infinity. So in one or another way, we can show that the solution is minus y pi integral from minus infinity to infinity f tau d tau tau minus x squared plus y squared. That is the solution. So we can use conformal or Fourier transforms or something. That is the solution. Another way to prove the solution is that we know it can be shown in general for general formulation. The solution of Dirichlet problem is unique. So if we present the solution and we show that this function satisfies the Laplace equation and the boundary condition, then that is the solution. Right? To inside the flow, inside the region for y less than 0, we calculate the Laplacian of that function by moving that Laplacian to the inner function, and we can show that this is 0 by direct calculation. It takes half page, but it's okay. For forming up, it's fine. Then the big problem is to show that limit phi x y as y tends to 0 minus. 0 minus, there are different notation for that. But 0 minus means that we approach the boundary from below, from the region. It's equal to f of x. This is a big problem. I mean, it's more complicated to prove, but still possible. It's complicated because if you just set y equal to 0, you can say, why in front of the integral, so it's 0. No, because if you set over here 0, y equal to 0, you arrive at the integral which doesn't converge. So you need to be careful with that limit. And the solution is that the interval of integration, tau interval of integration, you divide into 3 parts. So you cut that interval, and the length of this interval is x plus y4. So it's a little bit comes from nowhere, but yeah, that is something what people are doing. So, and then we can show that in this interval and over here, the that for this and that intervals, the integral tends to 0. Indeed, what's happening? Tau minus x in this interval is greater than this module 1 over 4. So you substitute 1 over 4. Here it's power 1, here 1 over 4, so it's square root. So here is power 1, here is square root. Is squared, so it's small compared with this number. This one divided by that one altogether it gives square root of y. So because the 2 minus x in this interval and in that interval it's bigger than this module 1. So then the limit, that limit is reduced to this integral. So we write limit phi x y, y tends to 0 minus, is equal to limit minus y, we can write it's module y pi, and tends to 0, integral from x minus 4 x plus 1 over 4 f of tau d tau minus x squared plus 1. And because for y, small y, the interval is short, so this phi, this f can be changed for f of x, and the rest of integral is calculated, and it's given it's a arctan of something, and it's possible to choose the altogether so, to deal with complicated limits, that is goes to 0, that is goes to infinity, so the 0, okay, that goes to 0 and that goes to 0, so 0 divided by 0, we cut that interval, complicated interval, and because it's small, we can approximate all other elements in this interval. So it's not just approximation, it's properly proved in the notes. But to prove that, we need something, we need now to know something about the function f. And that function f should, first it should decay at the infinity, because phi is decaying at the infinity, so the conditions of this analysis, f of x tends to 0 at infinity. Then the function should be integrable, minus infinity, infinity, f of x, f of say tau, d tau, less than finite, integral of the function is finite. It's actually it's just one condition, because that is followed from this one. And second, that is the interesting condition called Euler condition. This condition makes it possible to approximate a function over here with its value at the middle of the interval. This condition is that for any xy, x2, f of x2 minus f of xy 1 is less than a x2 minus x1 in the power lambda, where lambda from 0 to 1. And that is the Euler condition. It looks like continuity, but it's not. It's more, much more than continuity. In continuity, that is true for x and x1 and x2 close enough to each other. Right? But in Euler condition, it should be for any x1 and x2 from the interval, for any function, for any values. Right? So it's much more restrictive, and definitely the if the function satisfies this condition is continuous. It's interesting that if this lambda over here, that lambda in the power, a is positive, lambda is positive, but lambda is less than 1, it's shown over here. If lambda is greater than 1, the function is just constant. So there is no such function with lambda greater than 1. They do not exist. In particular function which is which is satisfies the Hölder condition, is square root of x in the interval from 0 to 1. And that function with the power 1 over 2. Now equal to 1 over 2. Yeah, for example. There are other functions also can be constructed. Okay, so then that is the solution. That is the solution. We proved, okay, not proved, but I showed that if we calculate the Laplacian, it's equal to 0, and if we calculate the limit, it gives the solution, right? Now, that is the solution, and here, let's see, yes, y divided by x, sorry, 2 minus x squared plus y squared is equal to a real part 1 over I, 2 minus z, where z equal to x plus y. So if you multiply by conjugate, numerator and denominator, and then take the real part, then these two they are equal to each other. If so, we can write that as a real part I integral from minus infinity to infinity f of d equals to minus shorter, right? Shorter. And this shorter gives us that integral. Just that one. Sometimes it's this integral is introduced together with the factors in front of it. Just that integral. It's now a Cauchy-type integral. Cauchy-type integral. This integral over a real axis, function f comes from nowhere, so it's given. In Cauchy integral, the function f is that one. So it's the boundary value of the function itself. Here it's not necessary, so this is why Cauchy-type integral is called. This function is this integral can be calculated everywhere except the real axis. On the real axis, it doesn't exist. We need to explain about the value of this function. So actually, the value of this function at the real axis, it's the limit of that function as we approach the real axis, and we show that it exists. But we need to look at that function more carefully. To do that, we introduce now definition. Definition, we are saying that the function of complex variable z is differentiable at a point if a certain limit exists. So f of z is differentiable at z if limit zeta tends to 0, w z plus zeta minus w z and divided by zeta, if this limit, so the standard limit for derivative, right, exists, and what's the most important part here? That one. However, zeta tends to 0. Doesn't matter how we approach the point, it's always the limit is the same. So that is the y, x, that is the point z, and it doesn't matter in which direction we approach this point, the limit is the same. Something similar you could remember from the function of real arguments. We can calculate the limit, or derivative And if they are equal to each other, we are saying the derivative is continuous, the function is differentiable at that point. Here, in addition to that and this direction, there are many, many directions. Right? And it makes difference, big difference. If a function of real argument, say f of x equal to, I don't know, cosine x is differentiable, that's the end. Okay, it's differentiable means it's smooth, that's the end. If function of complex variable, even that one is differentiable at each point, and that one is differentiable, then real and imaginary part of this function, they satisfy Laplace equation. So this means that to solve the Laplace equation, we need to find analytic function, that's all. So any analytic function such that the real part of the function and the imaginary part of the function, they are solution of Laplace equation, they are harmonic functions. Functions look like they are very special, right? Because the real and imaginary part, they are solution of Laplace, not at all. Any function which depends only on that, not on x and y separately, but only on that, they are the analytic function. Okay, there could be a special point where the function is not analytic. So the any function which depends on that analytic, for example, that function, that multiplied by conjugate of that, this is not analytic function. But it's nice, it's good function. It's x squared plus y squared, what you want, it's very good, but it's not. So we are not interested in that function. But we are in particular interested in functions like this, z minus I. 1 divided by z minus I. That function is analytic everywhere except at one point z equal to I. In the rest of the domain is analytic, so it satisfies the Laplace equation everywhere, I mean real and imaginary part of it. That function, z minus a tau, is also analytic function except at one point on the real axis, if tau is real, except at one point. Then, if we continue, the z function, here, minus, so this means that Cauchy-type integral is analytic everywhere except of the real axis. Below the real axis, on the real axis, everywhere it's analytic. If we change the limits and we say it's integral from a to b, f2 minus z dz, so tau, this is analytic everywhere. We are saying with the cut from a to b. In the whole plane, it's analytic except of that cut, except of the interval of integration. So in this way, we can say that the Cauchy-type integral is analytic function, means without any calculation, we can do calculation, but no need. If you know about the analytic function, no need to do calculation. You can say that the real and imaginary part of Cauchy-type integral will satisfy the Laplace equation. And in addition, we can, because we prove that the real value of that real value tends to f of tau as we approach the real axis. There also, in addition, something special about the analytic functions. Let me show over here. Let's say w of z is equal to phi x y plus I psi x y. And the function w is analytic. Then, because the derivative of that function is independent of the direction in which we calculate the limit, we can write dw dx. Okay, just differentiate in the vector x. Means we differentiate in horizontal direction. Also, we can differentiate in vertical direction only. So we keep x constant and we differentiate in y. So z now goes to iy. And now let's calculate each derivative. We calculate z1, so it will be phi x plus I psi x, right? And it should be equal to, and now we differentiate in y, it will be 1 over I phi y plus psi y. And real and imaginary parts should be equal to each other. And if you write that real parts with psi y and psi x equal to minus phi y, so you could recognize that it's so-called Cauchy-type relations. Means that imaginary and real parts of any analytic function, they are not arbitrary, but they are related by Cauchy-Riemann relation. Means if we know the imaginary part, then real part can be calculated by using that relation. If you cross differentiate this relation, you can prove that both phi and psi they satisfy Laplace equation. Okay. So to differentiate, for example, this function, we just in z, we just differentiate the integrand of the function. So we differentiate in z, and it will be the same integral, but now it will be tau minus z squared. And this is not singular because it's an integral is singular only on the boundary, but inside the domain is not singular. So we can do that integration. Now, let's return to the Cauchy problem. Now, to our problem. And we reformulate the problem a little bit differently. Just a little bit. Actually, from now on, it's good because we are not going. Actually, we did almost no calculations. Right? Yeah. Some calculations are hidden, but indeed they are not complicated. Like to find second derivative of certain function to show that this sum of them are zero. It's not complicated. But from now on, as I remember, there are even nothing like that. So the good point about the mixed boundary value program is that essentially you should do nothing. I like it. I like it. So let's say a formulation. Boundary value problem for analytic functions. Boundary value problem for analytic functions. Find analytic function of z in the lower half plane such that w of z tends to 0 as z tends to infinity, so on the infinity the function decays, and real part w x minus I 0 is equal to that of x. So x minus I0. Minus I means that we approach from below, from the origin itself. Where f of x is integrable and satisfy and we have the condition. So the solution of that problem, so this is the formulation. Find the analytic function such that the real part of this function is given on the boundary. The solution of that problem is equal to I minus infinity to infinity. This is what we showed. We use the Dirichlet problem. This looks at the solution. Now we this formulation just the same as in Dirichlet problem, but we work with analytic function and Cauchy-type integrals. So we proved that if we take a real part of it, if you take a real part of this integral, the limit is will be equal to the function in numerator. But there is the next interesting problem. Okay, that is about the real part. Real part of that integral, once we approach the boundary, goes to function f of x. What's happening with the imaginary part of the function? If we write w x minus I 0, what's that? Indeed, we can compute that it's equal to taking the imaginary part of this integral and saying that f is a real function. It's equal to 1 over pi, tau minus x, f of tau d tau, and the tau minus x squared plus y squared. Okay? So we need to find the limit of this integral as y tends to 0. And again, if y tends to 0, we can just and we divide one to another, and there will be tau minus x in. So it tends to 1 over pi integral. It's not good to write like this because this integral doesn't exist, right? So the if tau equal to x, that there is no such integral. But if we make the if we calculate that limit accurately, the result will be not that one, but very similar to that one. And I show only the result as y tends to 0 is equal to 1 over pi limit integral minus infinity x minus let's say epsilon plus x plus epsilon infinity and f tau d tau minus x and a limit as epsilon tends to 0. So you see, instead of the y, there is another small parameter as epsilon, which tends to 0, and the limit of the same integral, that x, we cut the infinity of x symmetric interval around the x value with small symmetric interval. So it can be shown that that is the true. Then, if this limit exists, then it's called principal value integral, Cauchy principal value integral. There is another things which we are going to. Cauchy principal value integrals. First of all, let's assume that this limit exists. First, let's assume that this limit exists. Then, w of z equal to phi plus I psi, and in the solution of that problem, phi x 0 equals to f of x, and psi x0, minus, I put minus over here, and this limit from below, is equal to, if I look at that one, 1 over pi integral from minus infinity to infinity, f of tau d tau minus x. However, this integral, that integral is understood in this sense. So we cut that integral of singularity, symmetric integral, and then we consider the limit as this cut tends to 0. If that limit exists, then it's denoted by principal value, we put it here in front of the integral, principal value integral. Okay? then you see what we can do now. We can write psi is the imaginary part. We can write imaginary part w x minus I0 is equal to 1 over pi principal value integral from minus infinity to infinity f. F is a real part. We write here a real part. W, sorry, tau minus I0 equals tau minus x. This means that imaginary and real parts of any, actually any function, analytical function. Now it's not related to any problem. They are these imaginary and real parts. They are related by this equation, which is known as Hilbert formula. Actually, it's known as the first formula. In shipwright dynamics, it's used a lot. It's known Husking okay, or something relation. Yeah, you calculate you calculate function on the for real frequencies, and then you solve that problem to find a solution for any complex frequencies, and also to find you find only the real part, and then by using that relation without solving any problem but just calculating that integral, you find the imaginary part. Real part give you the so-called edit masses as function of frequency, and the imaginary part give you so-called hydrodynamic damping coefficients. So which explain how much energy is taken by gravity raised to infinity. So that is the by that formula, which is valid for any problem. So then, okay, I'm not going to write it. There is the second formula, which is also easy to find. It's a real part is equal to the same integral, but of imaginary part. The difference is that there is sign minus in front of 1 over pi. So it's the second formula. Then, if you combine the these formulas and that one, real and imaginary part, you can find the so-called boundary values of the Cauchy-type integral. We use this relation and we multiply both parts by minus pi I. Okay. Then, in the limit, in the limit, it will be minus pi I. Phi goes to f of x, and plus phi integral plus pi and 1 over pi will cancel each other, minus infinity to infinity f tau d tau minus x. So the limit of Cauchy-type integral, as we approach the boundary means the that line of interval of integration, is equal to principal value integral. That's what we expected, but principal value, so it's understood properly in the right way, and plus extra term, without which comes, you can say, with residue of that function. You can think about it. That formula is known as Cauchy limiting values of Cauchy-type integrals. Right. Now, how about these integrals? How they calculated? In short, I will explain it. Indeed, it's not complicated. And actually, it's interesting that we can work with this integral in the same way as normal integral, without paying attention to the singular. Yep. Okay. So Cauchy principal value integrals. Then two definitions. First definition is first principal value integral from A to B e tau minus c is equal to limit epsilon tends to 0 integral from A to c minus epsilon plus c plus epsilon t d tau minus x. So that is the same limit I showed you before, and I said that if that limit exists, then it's known as a principal value integral. Now we are going to calculate that limit, but in simple case when there is nothing, it's just one. Okay, why not? See, that function is, we can find that integral there. Indefinite integral is equal to log tau minus x at c minus epsilon a plus log tau minus x. That is 1 divided by tau minus x. Integral is log b c plus epsilon equal to epsilon tends to 0. Limit epsilon tends to 0. Limit C. Yes. Limit we substitute over there is log epsilon minus log a plus c a minus c module, no need to write it, and so basically here a less than c and less than b. So that is the if c is not in that interval, the integral is not singular, but the result is the same. You will see. It's outside or inside, it's singular, regular, it doesn't matter. Big surprise. Plus limit b minus c minus log epsilon. And you can see this epsilon, that epsilon cancel each other. And this is thanks to the interval we selected is symmetric. So it specially was done in this way. And the result is log b minus c, c minus a. That is the result. And this result is the same if you just have no idea about singularity of integrals. So that is the example when doing mistake, you arrive at the right solution. Okay? Then, that is the first definition. And second definition is to say that, okay, if function, now we want to write the same integral but with numerator. Say f of tau. And f of tau, I'm not going to write it, but please just remember that f of tau is quite smooth function and satisfy that further condition. That is important. So then definition 2. Principal value of the integral from a to b. Tau minus c is equal to principal value of that integral is equal to integral from a to b phi tau minus phi of c tau minus c d tau plus phi c log b minus c minus a. So you see what we did. We extracted from the numerator the value of it at c, okay, over here. And now, if this function is smooth enough, in particular, it's well enough that Herder condition is specially designed to deal with such ratios, so it makes this ratio integrable. If the function is smooth, it's continuous, then this ratio is even has finite limit, but it's not necessary. It's enough that it's integrable. So this is not principal value integral, it's standard integral. So the function, z ratio, okay, it's complicated to integrate, it's defined, it's possible, it's limit. And the rest, then we add phi of c multiplied by the value of that integral calculated with phi equal to 1. That is the how these integrals are calculated. It can be, I mean, numerical values of this integral can be calculated in this way in particular. So there is example, there is a complicated example and a simple example. Okay, let's start with simple example. The principal value integral of minus 1 to 1 ax plus b x minus c dx. That's it. We can write it by definition, say, okay, pb minus 1, 1. Then from ax plus b, we should subtract that its value at c, so it will be a x minus c dx, and then plus value at c, a c plus b, and multiplied by by limit 1 minus c and 1 plus c. And that integral, you see, the x minus c will cancel each other. In particular, that say if phi, that phi is a sine function, that will be sine tau minus sine c. And the difference of sine, you can write as sine difference of angles divided by 2 multiplied by sine, as I remember, sum of the angle divided by 2. Right? And sine x divided sine tau minus c divided by tau minus c. It's a function easy to understand and to incorporate in the problem. Now complicated integral, but actually, okay, just to explain why that integral is shown. If you know that integral, you can solve the mixed boundary problem because so far we didn't solve it. But if you know that integral, you can do it. And that integral is partial principal value integral. And that is a strange integral. Very strange integral. Complicated, very strange. Principal value integral from minus 1 to 1 d tau minus x 1 minus tau squared. And this integral is equal to 0 for any x less than 1. Just 0. Singular integral, it's not 0, it's nothing usual has seen that y is 0, but it's 0. Yes. And to do this integral, it's possible to calculate it as it is by definition, but I suggest to go another way. We introduce this function, square root z squared minus 1. Actually, it's a product of two functions. And let me explain what's that. So that is the minus 1, that is 1. And then to calculate each of the square roots, we introduce the polar coordinates for each integral, for each square root. For that square root, we introduce the polar coordinate with r and the angle alpha. We calculate angle alpha in that direction, it changes from 0 to 2 pi. Then, for the second integral, we introduce another polar coordinate with angle beta and radius rho. Then we have -1 plus rho ei beta, and here z equal to +1 plus r I alpha. To calculate the first one, we use this representation. To calculate the second one, we use that. Why not? We calculate, and it gives us square root alpha rho e I alpha plus beta divided by 2. That is it. Where alpha and beta, they are from 0 to 5. Then we are concerned with the okay, let's find the value of this function everywhere. Everywhere it means we consider the plane. We take that interval from -1 to 1. And first we calculate the value of this function over here on the real axis, where x is greater than 1. For x greater than 1, we look over here, alpha equal to 0, beta equal to 0, right? So we substitute 0, 0, all together it's 1. And it gives x squared minus 1. Here, alpha equal to pi, beta equal to pi. Pi and pi. So pi plus pi, 2 pi divided by 2 is just 1 pi, e I pi equal to -1. And it's equal to here minus x squared minus 1. Now, what's happening over here? On this part, so there are two sides of this cut. On the upper side, alpha equals to pi, beta equals to 0, right? So it will be I, pi over 2, it's I, so it will be I, 1 minus x squared. On the real axis, the r and rho, it's just the okay, r and rho is always distance between 2 points, but on the real axis it's even simpler. So if one point is x and another point 1, so the distance between them either x minus 1 or 1 minus x, depending on where you on the picture. So this is why I'm writing this down this square root so easily. Then over here, it's what's happening over here? Alpha is still pi, but beta is 2 pi. And then it will be 3 pi over 2, and altogether it will be minus I 1 minus x squared. So the function our square root defined by using this cut, see, from -1 to 1, is continuous everywhere except for the cut, and on the sides of the cut it takes the values which differs by sign. So from that function we need, from this function, because we are concerned with the problem in the lower half plane, that is function equal to x squared minus 1, here minus x squared minus 1, and here is minus I, so 1 minus x squared. That is the value of r of z, x minus I0. That is the value. That's all. Actually, we solved the problem. Now we need just to put things in the right place. In the right place because because of what? Because of that. W of z is defined now as z squared minus 1 minus z. Let's consider this function. This function tends to 0 at the infinity. Right? This behaves z, and this minus z altogether is 0. Then a real part, so it's x minus I 0, but a real part is equal to, for x greater than 1, this square is real. This z is real. Right? And multiplied by I, real part is 0. This square root is real over here and over there. This z for y equal to 0 is just equal to x, is also equal to 0. And for x less than 1, it will be, okay, z is still gives 0. I multiplied by minus I, so altogether it will be 1 minus x squared. And if we calculate the imaginary part, but only where x less than 1, imaginary part. So if x less than 1, so that is the imaginary. With this I give a real contribution. So imaginary part comes from over here, and it's equal to minus my x. Okay, minus x, because it's imaginary part over here, so we don't need to write minus x. Now, we still remember the Hilbert formulas, and Hilbert formulas is saying that if you take a real part of the function and integrate it, but now a real part is non-zero only from minus 1 to 1. You take a real part and integrate where it's not 0, 1 minus tau squared, so minus x, and we put PV and 1 over pi. So z1 should be equal to imaginary part of the function. And that imaginary part is minus x. Is equal to minus x, where x less than 1. And now what we need to make some algebra with this integral. So we are doing it like this. In that integral, we multiply numerator and denominator by square root, and it gives minus 1, 1, 1 minus tau squared, tau minus x, d tau, 1 minus tau squared. Only that integral. And that one is already something similar to that, right? Then we, that 1 minus tau squared, we write 1 minus x squared plus x squared minus tau squared, why not? Right? And it gives us 1 minus x squared integral minus 1. Okay, that is without principal. So it's only, we deal with that integral only. So the PV is outside. And it will be d tau, tau minus x squared 1 minus x squared. And what's that? Because it will be x squared minus tau squared divided by tau minus x. It will be plus minus x minus tau, no? Oops, sorry. Minus x minus tau. No? Yeah. So now that integral over there, this one, is already in the form we need. Now we need to calculate that integral, but it's normal. It's a okay. It's a singular, but so-called improper integral, so it's okay. And also we know that this tau gives 0 because this tau, with this tau, the function we integrate is odd. And the interval we integrate is symmetric, so that integrals are always 0. So the only what remains is minus x and integral from -1 to 1, 1 divided by square root, and this is equal to pi. Now, 1 over pi cancel, minus x cancel, that integral is 0. That integral is 0. That's all. So now we completely equipped, and now we can solve any mixed boundary value problem. First, we need to formulate it. We formulate it again like this: mixed boundary value problems for analytic functions. In this mixed boundary value problem, our interval is our boundary is divided into pieces. On one of them, a real part of the function is given, of unknown function is given, on another part, imaginary part is given. Actually, any problem could be transformed to that. I'll show you. So, okay, formulation. Find W of z in y less than 0 such that W of z tends to 0 as z tends to infinity, and real part W x minus I 0 equal to phi 0 of x greater than 1. So again, it's kind of example, because I still dealing with the interval from -1 to 1. But any other intervals, it's not a problem to generalize these results to interval of other dimensions. And actually, in practice, to solve the problem for different intervals, you just use the stretching and the transformation to return it to -1 to 1 using the formula. But if you want, you can solve the problem once again. If you know how to proceed, then you can find for each problem your own shortcut to the solution. And such that, okay? And that is the for x less than 1. For x less than 1. So that is the, I would explain here. For example, that problem with phi y equal to -v, phi equal to 0, and phi equal to 0, delta to phi equal to 0. So that is the problem I showed you, and I said that is the problem for floating up and floating left. Right? So this problem can be reformulated in this way if we differentiate the condition of the free surface in x. We can do this, right? X. And then we say phi x minus I, phi y, that is analytic function. So we need to find that analytic function. You can say, yeah, it's complex velocity in lower half plane such that the horizontal velocity is equal to 0 on the free surface, and normal velocity is given on the plate. And now you are saying, yes, the z phi 0 for that problem is 0. Real part is phi x, is 0. And the imaginary part corresponds to minus phi y. You should not forget about that minus. And means that psi 0 is v. So always we can do like this. Either from this problem, because in the notes there are several, I believe, 3 approaches just to give different ways of deriving, of moving from the original formulation in terms of the real functions to the formulation in terms of the analytic function. Because of symmetry of that problem, we can say that the vertical axis, which goes through the center of the plate, is the symmetry line. If it's symmetry line, it's same line. If it's same line and goes to infinity, the string function on this line is 0. If it's 0, it's 0 also over here. That condition phi y can be turned into the condition by using the Cauchy equations to the psi x on the boundary, and we can integrate the boundary condition on the solid surface. It's always possible to write the dynamic body boundary condition in terms of the string function in two-dimensional case. And then the string function is given on the solid part, and the function itself, phi, sorry, not function itself, but phi, potential is given on the contact on the free surface, and then it's again the mixed boundary problem of analytic function. So, okay, that is the problem we want to solve. To solve this problem, we use that function out of that. This is in the example, we didn't give name to this function, just said, yeah, it's an interesting function, let's try. But it's called a characteristic function of the intervals. Right? So that function is equal to 0. That function is imaginary inside the interval, and it's real outside the interval. So now, if we consider product, the product is again analytic function, a product of two analytic functions. So we do not need to prove that it's analytic or to check the Cauchy-Riemann equation for that. No need. The product of two Cauchy function is again analytic function. Then the on the real for x for x greater than 1. It's not convenient to write it over here. Let me use this part. So now I want to calculate a real part f x minus I 0. So real part of the problem. And first, for x greater than 1. For x greater than 1, f is equal to, R is equal to x squared minus 1, and w is equal to, real part is phi 0 plus imaginary part of w x minus I 0. If so, then the real part is the product of these two. So the real part is equal to square root x squared minus 1 phi 0 of x, where x greater than 1. Right? Next, so I use this line for calculations only. So then, if x from minus 1 to 1, over here the product r is equal to minus I squared 1 minus x squared, and the for w only imaginary part is given, so it will be a real part w x minus I 0 and plus I psi 0 of x. And you see the real part of that product is equal to minus I give plus, so it will be 1x squared psi 0 of x, for x less than 1. And similar, we obtain x squared minus 1 psi 0 of x for x. So the w is solution of the mixed boundary value problem, but that function big R, I still didn't get name to this. Oh no, it's Cauchy function. But it's better to say it's magic function. Because it's if you know that function, it turns the mixed boundary value problem to odd name problem. we can use it Cauchy-type integral, principal value integral to write the solution. So it's magic function. Because now, for this product, big F, the real part is given. Right? So the either imaginary or real part of the original function W were given on the boundary. Now, after we multiply, after we made that product with a magic function, now for big F, which is analytic function in the lower half plane, imaginary real part is given, and we can write its solution. So it's solved. Actually, almost nothing left. Huh? Oh, we still have some time. Okay. Unfortunately, it's not the end. Unfortunately, it's not the end. And the solution is not complete. Because if you write the solution, okay, the real part is given, right? So we can write the solution is z equal to I divided by pi, integral from infinity to infinity. So that is the solution of the derivative problem, which was shown already several times. Unfortunately, this is not there, but still we need to know something. Okay? So that is the solution. But that solution, that integral, it tends to 0 at infinity. This product is not necessarily tends to 0. No. Because if R, so this so it's better to say that this is particular solution. F particular tends to 0 as z tends to infinity. However, R behaves as z. R behaves as z at infinity, and W, if in this term, it behaves as big O 1 divided by z at infinity. And z tends to infinity. It can be shown the behavior of infinity. So the product, actually, the product tends to a constant at the infinity, but not to 0. So this means that actually we didn't solve the problem yet. But there is a hint, and the hint is about, it's about again that eigenfunctions I mentioned at the beginning. Because this problem, there are many eigenvalue solutions, and we can use this solution to solve the problem completely. For example, that is the problem says real part of the function of w x minus I is equal to 0, imaginary part x minus I equal to 0, and real part also here 0 equal to 0, and w and z is analytic. This problem, all conditions are 0. This problem is a non-zero solution. And that non-zero solution, let me try to write that solution. It's equal to, for example, that one. I z squared minus 1. You can recognize it's a special, special characteristic function, z squared minus 1. So it's real on the imaginary, or is real on the, say, this semi-infinite part, but now being multiplied by I, it's imaginary. So indeed, this function satisfies these two conditions. It gives real part of it is 0. Over here, the square root is imaginary, but we multiply by I, the result is real, and it satisfies that condition. So any function like this, any function like that, and any function like z squared minus 1, say, over 2, then 11 over 2, 1001 over 2, all these functions, they satisfy these conditions. So they are so-called eigenfunctions. Also, if we make functions like this, it's also, so you can argue, okay, it's not a good function because the infinity behaves not good, it doesn't decay at the infinity, that one decays at the infinity. But it's singular at that point. And this is explained why the functions are the solution of mixed boundary problem are singular. This function, okay, So the proper behave at the infinity, but it's singular. However, they give solution, because that solution we calculated, it's not complete. It doesn't satisfy the condition at the infinity. So we need, I mean, that one, because it decays at the infinity, and in our solution it should go to a constant. Right, and this constant actually can be specified, or should be specified, in addition to the formulation. So in terms of the big F, because the real part of F is given, so we can say that general solution, we can add any function like that one. C0 is real. C0 is real. Imaginary part, we don't change imaginary part by adding any imaginary. We do not change real part adding any imaginary constant. This is also doesn't change real part. And in general, it's Cn, Zn, I. Any combination like this, where Cn are real coefficients. All of them on real axis, z goes to x. So Cn multiplied by x, x in the power n is real, and we multiply by I, so the result is imaginary. So there are many solutions. So this is one of the problems, and what's happening once we solve the mixed boundary value problem, that solutions with high singularities, because finally, to find the solution, we take big F of z and we divide it by z squared minus 1. Right? So that solutions which are singular, they can be attractive for the solution. Once we go to the numerical, then the solution breaks and we cannot continue. Right. So this means that in addition to our solution, our solution should be supplemented with the several terms or terms with unknown coefficient C0. This is what we are going to do. I remember this formula, so I should write it once again. Over here, and that is the final warning about the mixed boundary value problem. That this is the solution is singular. Then solution is not unique, and we need to that is very different from the boundary value problem. We need to specify class of the solution. We need to specify which solution we are looking for and which singularities are allowed. Right. So W of z equal to f of z, the R of z equal to f t of z plus I C0 plus I C1 z plus so on z squared minus 1 equal to. Okay, the W should go to 0. Z1, which this is the integral, it's on itself goes to 0 and divided by square root, definitely goes to 0. Z1 also goes to 0, but Z1 not. So this means that all these terms, we do not account them, and we arrive at the solution with one constant, Z0. But Z, you remember, in Neumann problem, we had one additive constant, so we can add that constant to the solution. So now it's more complicated, it's the whole function. But the function, we know that function, but okay, we need to know that function, and this function is multiplied by the coefficient. Okay, so then the complete solution is, not the complete, but not unique, I minus infinity to infinity, real part, f tau minus I0, d2, tau minus z plus I C0. So, the result is, in general, general solution is not unique. We can find the solution, and it's not unique and singular. W of z is singular f z equal to plus minus 1. And the domain is perfect, it's half plane, so the straight line is could be the most smooth line in the world. Then it's nothing about the boundary conditions. I mean, are they smooth or not? Are they singular or not? Okay, it's singular not allowed. But even they are perfectly smooth, the solution is still singular. And it's singular at 2 points, plus and minus z. Z equal to plus and minus 1. Right, but there is that constant, 0, and we don't know that. So we can choose, we can say if w of z, w of say plus 1 is finite, then we can find C0, right? If we impose extra condition, our function is finite, but only at one point. We cannot claim we can find that it's finite at 2 points. If it's finite at one means if we put here 1 and calculate that integral, its value is equal to minus I C0. So we can find that value of C0, right? But only at 1. So then we can find this constant. However, W minus 1 is unbounded. Okay? So either we work with condition, we work with function defined up to the constant C0. Either we we specify this constant, but we can require that the solution is finite only at one point. No chance to satisfy the condition in both points. So this means the solution always, either over here, either over there, always it's singular. It doesn't matter how smooth are the conditions.
For the impact problem, plate impact problem, that is on the both sides.
Yeah. So now, if we, due to some reasons, we want to make, we are looking for the solution which is finite at both points. There, finite at both points means that if plus 1 and minus 1 are finite, if it's in both ends, they are finite, then the boundary condition cannot be arbitrary. Then psi 0 of x and phi 0 of x in the boundary condition, in the boundary condition are not arbitrary. And there is the relation. Okay, so what you're doing, you set this bracket at z equal to plus 1, 0, because it should be 0. If not, then it's singular. Right? You set it 0 at plus 1. Then you set it 0 at minus 1. The values of integrals are different, right? And then you find C0, and in addition, you find the condition for the boundary values. Right? So this means for the solution to be finite, the boundary condition, the condition of your problem, cannot be arbitrary. That is the point. So this means the general case is singular solution.
In the case of the impact, you actually have infinite velocities at the corners,
Yes.
no?
Yeah. So if you go to the impact of the plate, right? If you go to the impact of the plate, phi x equal to 0, phi y equal to 1, minus 1 is phi x equal to 0. So then you make the product. Okay, like that. And you are saying that the real part of this product on the boundary real part of the product of the boundary, you calculate what's that. On over here for x greater than 1 on both sides, phi x is 0, so this part is imaginary, that one is real, so altogether it's 0. On the plate less than 1, phi x is not 0, but that is equal to minus I1 minus x squared. So to find real part, we need to multiply by z. Minus I by minus I is minus 1, phi x equal to 1, so altogether it's 1 minus x squared. So real part of this product is equal to that one. So then let's calculate this one, but imaginary, but only at x less than 1. So to find what's happening over here on the plate. The imaginary part on the plate, that is minus I. So minus I we should multiply by z1. So it will be minus phi x 0 square root 1 minus x squared. And then we use the first inverse formula, which gives us that imaginary part, which is minus phi x 0 1 minus x squared equal to 1 pi minus 1 1, and imaginary part, real part, so squared the tau minus x. Okay, and PV. And actually, this integral we calculated already. I don't remember it, but we calculated. Okay, we did it. So, but here, what's happening over here? In this problem, phi x minus I phi y, this infinity behaves as z squared. And once we multiply by square root, the product behaves as 1 over z. So that is the complete solution. There are no arbitrary constant, additional constant. However, that integral has finite value, non-zero values at both x equal to 1 and plus and minus 1. Non-zero values. And then, to find phi x, we should divide by square root. Right? So then, without calculating for this integral, I know that it behaves as 1 divided by 1 minus x squared as x tends to 1 minus. Okay? So that is singular. Right? So the horizontal velocity is singular. So if we calculate imaginary part over here, it will be equal to phi y. And the same integral, and instead of that one, it will be x squared minus 1. And we divide it again, and we find, as you said, phi y is singular over here. But also the velocity over there under the plate horizontal velocity is also singular. So the good point about these formulations with the flat plate and impact is that it looks simple. I mean, formulation looks simple. However, in terms of the regularity, they are not good.
In terms of physics, it is also not.
In terms of physics, something is missing. Yeah, it means something is missing. Like over here means actually once the plate penetrates, so there is that jet which cannot be described by simplified conditions, because that is a very simplified condition. Over here, once we write this condition, we do not account for nonlinear terms in the dynamic boundary condition, right? This is why it gives the problem. On the other hand, once we simplify the problem, we solve it, and then we can find if it's the result not physical, that actually it's not physical only close to that point. Then we go to that point by using the asymptotic methods, and we formulate a local problem or a local problem of the flow in the iteration and solve them. Right? So the solution, yeah, it's not valid in that point, but it's very nice over here. It's a well described the shape of the free surface in distance from the plate. Right? But locally, and also in terms of the forces and other things, it gives something, but not everything. It can be done better, right? But on the other hand, it's kind of simple. It's simpler. So the in particular for that in that condition, not in that condition, just a moment. No, in this problem there is it's no difficulties with the C0, with the constant C0. However, if you formulate this problem not in terms of the velocity potential, but in terms of the complex potential, then there will be that C0, and it can be shown that the condition of finite, then that in the boundary are not arbitrary, but they are not arbitrary, but due to formulation they are such that these functions they are odd, so they are even. And even they are, they are odd. They're odd. And if phi 0 equal to 0, then the condition which provides the final solution is that one. Psi 0 of tau, d tau, 1 minus tau squared equal to 0. So this is standard type for all these conditions look like that. So the some integral equal to 0. That extra condition, which provides the final solution, boundary solution, it doesn't, it says nothing about the values at a certain point. It speaks about the global value, like that integral over here. And again, okay, if we formulate the problem of impact for velocity potential, we say for velocities, then velocities are allowed to be infinite in that sense. But if you formulate for, say, displacement potential, means integral in time, you can do this, but displacement they should be finite, right? And then this condition gives the equations for the size of the vegetarian. So they actually define the solution how it behaves. Yeah. Any questions? We still have 4 minutes. So it was challenging to squeeze the 20 hours lecture. For 20 hours, they spoke for second year students. So it was very slow, quite slow, but still complicated. But and also the part about the conformal mapping is missing. Yeah, it's about 4 lectures about the conformal mapping. How once we use conformal mapping, what's happening with the formulation of the problem and how to proceed.
What if there are holes in the domain? Can it be handled in a similar way, or if there is submerged body, for example?
Yeah, but everything should if it's a free surface and submerged bodies, right, the conditions are not mixed boundary value. The conditions are different. On the free surface, one condition. On the body is another condition. Right? But these boundaries, they do not intersect. Right. So this is this is say only for floating bodies when there is that contact point. Yeah.
So the domain has to be just. It has to help.
It has it has to be.
What is the correct term for
simply connected. Simply connected. Yeah, simply connected. So it's holes are allowed. So with the holes it's okay. I mean, if you solve problem like this, for example, it's okay. But still, it should be derivative and function they specify on one boundary. Over here you can over here it can be say like for bubble the potential is equal to constancy or given on the bubble, and that is the phase surface where something is floating. That is the so mixed in that term because the
Yeah, that's what I.
yeah, because
didn't
there are
mind.
different type of mixed problems. In particular, if we consider say that is the this is the bottom, this is the wall, and that is the phase surface, right? So there is the condition on the phase surface over here. Condition on the wall is different, right? It's on the normal derivative, normal velocity, and condition also normal velocity. So this problem also we can say it's mixed boundary value problem. Indeed, it's mixed boundary value problem. So the normal derivative given over here, over there, and quite complicated if we account for gravity, complicated conditions, so the condition over there. But this problem can be solved because of that special geometry by separating variables.
So you say that in initial that the boundary must be smooth, but
Yeah.
that is not
Yeah.
And also that there are two
On the
boundaries.
other hand, let me say something more. On the other hand, if we take our problem, if we take say this is our problem, and this is the boundary with normal derivative, say gamma 2 phi dn equal to g of s, and that is the gamma 1 phi equal to f of s. And by conformal mapping, potentially, we can map it onto that region. So such that these two are gamma 2 and with normal derivative only. And this that one, it will be gamma 1. From that point to infinity is gamma 1. It's possible.
Conformal mapping save the angles.
Yes.
And that is you have a corner in the so that is was no
Yeah,
corner.
there will be singularity of the solution. Yeah. But
But it is not
the
conformal mapping from the smooth line to the corner.
no. The like this angle, you can always map it onto the plane, right?
Yeah.
So if it's a pi over 2, then we are saying this is z. So z squared. Z squared. So this is okay. It's better, I think. So let me. A little bit about conformal mapping. So this is the that is the region, right? That is the region, and we want to map this region onto the upper plane. So that is the say that, and this is zeta. So mapping is zeta equal to z squared. That is the mapping. So that one over here is iy. We square it, and it goes to negative imaginary axis. Positive axis goes to positive axis. However, the point, the conformal mapping is there should be both sides way. So if you go to inverse, it will be z equal to plus minus square root of zeta, and that has a singularity over here in terms of the derivatives. But indeed, as Tanya said, the angle, which was pi over 2, now it's pi. So then we should expect problems. Should expect problems. But that problems is very much related, with the Kutta-Zhukovsky condition. For Kutta-Zhukovsky condition, that is the profile, aerodynamic profile, and we map it onto the circle, and at that point, the turning edge with a certain angle in goes to pi over 2. And then the conformal mapping is singular, but this singularity is used to specify the circulation around. Circulation plays a role. Actually, it could be the same. C0 circulation. So the circulation for circle circulation can be any. I mean, around the circle. Right? But for if you use the same circulation for this profile, it in general gives you infinite velocity as a trailing edge. Right? But only if the circulation is right value, so it's similar to that C0, then it's finite at that point. But in this problem, there is one singular point. In our problem, we consider there are 2 points. However, also as I said, this technique was also not the use suggested that conformal mapping onto the special domains like that, and then we can use the separating variables. Yeah, but it didn't turn to be,
Actually, you can use the strip function and the potential as variables, no? Because the strip function is equal to 0 in the whole, on both walls.
Yeah. Yes. Yeah. So there's and in terms of the three-dimensional problem, it's a completely another story. So just for circular, not axisymmetric problem. It could be a non-axisymmetric problem, but that pieces at which the different conditions are imposed, they should be circular. Like circular disk. But for circular ring, it's already almost, I don't know how to solve this problem. But interestingly, if also for elliptic shapes, it can be solved there, but there is a special function elliptic. No, the Lamme function, we call Lamme function. They are functions for they used to describe the vibration of ellipsoids. Once the ellipsoid is squeezed into the plate, so ellipse vibrating moving. So that is not many. In general, it's not many. And also, if you visualize this problem and to solve it numerically, and if you Google Scholar or anywhere, it's difficult to find papers on that. It's complicated, but because if you can kind of decompose problem to divide it into the geometrical problem of conformal mapping, and then after the conformal mapping, the solution essentially is just given by integrals. Right? So this means we can control accuracy. Even the integrals are not perfect, but it was explained how to solve them, how to make them regular, and to solve them. It's possible. Right? So then complicated problem, you think, okay, that is the one difficulty with conformal mapping, but there is no another difficulty, because after conformal mapping, our problem has the analytic solution. Okay, it is integral, but the solution. That one. Yep.
Okay.
Thank you very much.
Prof.
Thank you.